should be pretty much out of the box working.
And are you working to ES5 or ES3 or?
We're doing ES5. We would like to be on ES6, but we just didn't want any. We didn't want to, because we're like a module used across, whether you're running on television, browser, whatever. We didn't want to have to enforce whoever's developing against us to have a transpilation step if they're just simply requiring us in, as opposed to using our artifact. So.
Yeah, and to your point, the devices that you'll have to support, a lot of those will go down to ES5. I don't know if they.
Yeah, we'll never be able to run ES6 on a lot of those devices because, you can't update devices already in the field a lot of times. So,
yeah,
it's not like we can just give them a new Roku or a new Xbox One and say, hey, let's start. Here's a whole new piece of equipment that supports all this. Not an Xbox One, but any of the here's a new television. Congratulations, you can now use ES6. So it's just easier if we don't. All of our pretty much everything in Netflix uses some form of ES6. And we have transpilation processes, but we just didn't want to force people who require us in to have to do that.
Right.
And so we chose ES5. And you also have way finer tune control over performance if I am the one doing this. Because whenever you go through a transpilation step, you don't necessarily know how much code they're going to transpile from an ES6 feature to an ES5. Maybe it's not optimized for our platform. Maybe it is. I don't want to have to go through the lengthy process of investigating all that. It's just much easier to write the stuff I know is correct.
I think that's what I was trying to get at, but I didn't articulate it as well.
Okay, my bad.
Was that no, my bad. So that's it. That's really cool. Sorry to interrupt, though. Keep going.
No. Thank you. Those are better questions, anyways. Hopefully, this is all making sense. It's a lot of code. I get it that I'm probably not doing a very good job explaining all this.
So it's easy. I just with some of the file names, we need to make sure that we understand where we are in the code, I think.
Okay, yeah. So we're still in walk path, which, just to recap from our previous little discussion there, that you go through get.js inside lib/get/get.js. You go through that. It'll take each one of your requested paths and puts it through this walk path algorithm. Walk path is found at walkpath.js. So we've just described our inductive case or our base case, which is there's nothing there, there's a type, or we've reached our maximum depth. So then we report the value and return. Whether it's an error, it's missing, or it's an actual value, we will report it. So now we're going to do our inductive step, where essentially we just assume that we call it a key set for now. So we grab whatever depth we're at. So we start at 0. So we grab the first item out of our path. So we're starting at our root cache with the first item in our path, and we're going to start evaluating from there. We check to see if this is an object. If it's an object, we need to do more stuff, because essentially how you can think of it is when I request foo bar baz, I'm requesting one value, even though I'm requesting with 3 keys a single value. But if I'm requesting foo 210 baz, then I'm not requesting one value. I'm actually requesting 11 values. I'm requesting foo 0 baz, foo 1 baz, foo 2 baz, all the way up to foo 10 baz. And so we have to know this. So when we do our depth first search, we have to be able to kind of branch on that. Interesting side note, I actually, at least for our devices, some people might already right away see, well, you don't need to recurse if it's simple keys, meaning you should just be able to do a for loop until you hit one of these branching places, and then you could actually do your recursive step that way. I found no performance difference in Node or on device, either doing it recursively or iteratively. So that's, a function invocation is clearly not our bottleneck here. It's the entire algorithm is the bottleneck, not that. Just fun side note. So anyways, so we determine, is this key a complex key? Does it have multiple values? We grab our next depth. Iterator note is essentially, I don't want to litter input, meaning I don't want to attach hidden values to an array or an input they give me. I want to keep whatever the user gives me clean. And I just keep the side note that I will be able to do, that I'll be able to know where I'm at in my iteration if it's a complex key. So if we're a complex key, we'll essentially create this iterator set. So I hand it my key and I hand it this blank object note, and it'll store a whole bunch of information and give me back my key. Else, it's just the key, meaning that it wasn't complex key, so it's the string foo. Then we go on. So now that we have our key, we're about to work here. We kind of hit this really odd thing that can happen. Someone can, since you will eventually programmatically generate paths, you could accidentally programmatically generate something like this. Lolamo and empty array summary. Like that doesn't make any sense. There's nothing there, right? That's an empty path. So if that happens, we just simply return. It's kind of one of these, we have a second base case, but it is only if there's an error along the way. So here we go. So now we're about to enter the main part, the recursive, kind of like our inductive case. So we have all of our setup stuff. We know what key we're operating on. We have our iterator note set up in case we're going to go over multiple keys. We're just ready to go. So I set my next optimized path length. I went through a period of time where I really, really, really want to be verbose on my variable names. So optimized length +1 is exactly what I'm doing right here, just in case. So we start off on the top of this do while loop. So why is it a do while loop? If there's, often we don't use do while loops, but if this is a simple key, we only need to do this once. If it is multiple keys, then we need to go over this a bunch of times. So at the very bottom of our do while loop, essentially we have this little check here that goes, if there is an iterator note and we're not done, we're going to get the next key. And then while that's not done, go back up and do this over and over again. Keep on recursing for every single key in your key set. So okay, so we have the key foo, and let's just kind of actually, what'd be kind of a fun little thing right here. Let's just do this, open this up. Sorry, 1 second here. Let's just pretend our cache looks like, let's just give it a name too, so it's proper, is foo bar baz. So that's our cache. And we're doing a model dot, get foo bar. That way it might be a little bit easier to kind of have these things in line. So now currently our key that we're evaluating is foo. And so from reference is false. We haven't gone through a reference yet. Our optimized path is empty right now. Our requested path is empty because we haven't traveled in our cache at all yet. So this is kind of a throwback from, actually I just realized that as we're going through this is a throwback from one of our older notions that you could have a null key. Don't worry about it. I should probably technically do that, but we haven't done that yet. So we'll just keep that in there because I don't like to alter code as I'm doing live podcasts.
Push it live while we're doing this.
That's a great idea. I think I should do it. So we essentially take our current, take our key, and we create our next. We take our optimized length and we set that as our key. So this is the whole crux of the ability to not copy arrays while we're doing this, is that because we know our optimized length at the beginning, we can just keep on littering it. And as it goes through this walk, it keeps getting bigger. But since we're using these defined stack variables, we will always iterate on the same value. So if we have a complex key, we will alter our requested path at the current depth every time. Even though our requested path could be 10 keys long, we could be editing the first key right here. And so it's a little trick we use to avoid copying. So we set our value. So we have foo. Oopsies. Foo. So our requested and optimized path become that. And we set essentially our next optimized path and our next length. And then if there is a next, we check to see if we have a type. If our next depth is less than our path length, and there's a type, and the type is a reference, and it's not expired, then we need to follow this reference. So why is the next depth required to be less than the current path length? The reason being is that if you request, say, foo bar, let's go back to our little in cache example here. Say it is a type, ref, and our value is, we're going to go to baz. And so we actually have this other place in our cache called baz. Yeah, there you go. But what we don't want to do, if you request foo bar, we don't want to follow that reference. We want to give you the reference, is essentially what you're asking for. And so this is one of those things where we only follow references if our next depth is not exceeded the length, meaning we still have one more key left in our path to evaluate. So we go here, and we're just going to skip this because right now in our little trivial example, foo is not a reference. So we don't have to do that. So now we start with our production of output. So how we produce our output is when you request you know, something like foo bar, eventually, see, our output is gonna look something like this. You know, foo bar, and right now we actually inserted a reference. So we'll keep on making this a little bit more trivial. There we go. So let's add this little item to it. There we go. So now, eventually, if we requested that, our output should look something like this. That's what we would expect to come out, because we requested foo bar B, and we should see the keys in our output foo bar B. It just makes sense. And so what we're doing here is, at every level in the depth search, we're going to recreate our output object. And these extra little private things that we're adding are for dereference, which is that bound path at the beginning that I was describing, where you could latch onto a spot in the cache. Which, I mean, once again, that's just a large amount of things we would have to go over. So just trust me, we need this information. Just have to have it. So we attach this little object we're creating here to our branch info at this depth. So that way, if we request a key that has like a complex key and we have to produce, say, 11 paths, and we don't have to recreate this object a bunch of times at every depth, we only have to create it at every time we need it. So if that object exists in our output, it will exist within this branch info. If it doesn't exist, so if we had something, I'm kind of getting myself a little ahead here. If we had some multiple argument item here, we wouldn't create the foo object multiple times. We would simply just create it once. And so it's one of these kind of optimizations we had to make, where we're creating output essentially as we go, but only the dereference information. It's probably not a good explanation, but you get the idea. We store this object at every depth as we go. So then once we've set up everything, we're going to just re-walk our path again. But instead, we're going to walk our path with the same model, the same root cache. Instead of current, we're going to use our next place to walk. We're going to use our same path, our next depth, the same seed we need to fill in all of our results, the actual function output in case there's missing paths. We need to add a bunch of stuff to that, like little the actual fragment we emit out of get.js. Our branch info, so as we recurse down, we can keep on adding more of these output objects. Our requested path that the user is actually asking for, our next optimized path, and our next length, and our, if it is JSON output, and if we're from a reference. Now, if we followed a reference, this is the only place that we actually have to copy anything. It's because when we follow a reference, we cannot use the reference in the cache and just say, okay, this is my new optimized path, because I'm going to add more keys to it, and it essentially break the reference next time we try to grab it. So that's why we have this next optimized path, next this, or next optimized path length, is that we may have to copy it. And if we don't have to copy it, it's just simply optimized path length +1 and our current optimized path. So now we do our next walk, which our next walk is going to be, we just got done evaluating foo. Now we're going to do bar. And bar is a reference, but let's just get up there. So now we get up there. So is our current place in our cache, is it not there? Correct. It's not there. Oh wait, we're right here in the cache. Sorry, there we go. We're right here in the cache. Do we have cache? Yes. Do we have a type in the cache? No. Is our depth equivalent to our length? No. So we're going to just keep on going. We need to keep on evaluating the cache. So we set up our key again. We check to see if it's a complex key. It's not a complex key. Is it an undefined key? Does it not even, like, is this a poorly generated path? No. All right, so we're going to set up our next optimized path length, which is going to be 2 at this point, optimized path length +1. And we're going to start our loop again. So this time we we grab our next, which this time we use our current key, which is bar. We add it to our optimized path, bar, and we add it to our requested path, bar. We set these default variables for our next walk, and then we go, okay, there is a next. It does have a type, so we grab the type, we grab the value off of it. Is our next depth less than our path length? Yes, because our next step is 2 and our path length is 3. So we're good. Do we have a type? Yes, we do. Is it a reference? Yes, it is. Is it expired? It's not expired. So now we need to follow the reference. So following references is similar to the path walk that we're doing now, except for it's simplified. It doesn't need to concern itself with as many edge cases. It just simply needs to go all the way through. No reference can contain a reference as you're following it. You can only land on a reference once you've exhausted the first reference you've followed. So there's like a lot of nice little rules that make things just simple to do. So once we've followed this reference in cache, which it's just simply Baz, so we go up here, we get to Baz, we now have our next place in cache we need to go to. So we pluck that off of our reference we've followed. We set our reference path, which is our new optimized path, which is Baz, and then we clone it over. So now our new optimized path is as, and our requested path remains foo_bar. And our next optimized path length is, let's see, next optimized, or we'll just call O length is 1. Now we've reset these variables. We recreate our output with all of our dereference information. We put this at our next depth. So now we have 2 different objects we've created along the way. And we rewalk again. So now we're right here in our cache. We have these set up for our optimized path, our requested path, and we're going to go through once again. So we go up to the top. We haven't hit our inductive case yet, or our base case. So we go to our inductive step. We set up all of our key information, which it looks like it's B. So we're going to replace this with B. It's not a bad key set. It's just fine. So we can go into our loop. And then from there, we'll add B to our optimized path and B to our requested path. Go through here. It's not a reference. We can skip all this. And we add the output information. And then we walk path one last time. At the end of walk path, we do have a piece of cache. It does, essentially what this would actually be inside the cache would actually be something along, I technically lied, but it's okay, just to make things simple. So all of our actual values are wrapped in this sentinel types. So it does have a type. So we can now go on and we can report this value, and we're done with this like branch in our walking logic. So do you want to go to value type?
It's interesting. Before we do that, that sounds good. But before we do that, like, I'm really surprised with all the edge cases and all of the different possibilities that are here that you have so little code on this page. Like, there's not as much if conditions as I would expect. So when you initially did this stuff and you were going through, how much longer were these files?
Tremendously longer, actually. Well, so the funny thing about recursion, if you don't take some time to think about it, it actually can become really sucky to work with. So the nice part, what really made this cleaner was reversing how we do our checking. So we do our checking for our base case right away, as opposed to first evaluating the path, getting the key, getting our next item, and then checking if we need to leave. If we do it that way, it's an explosion of if statements. I mean, there was literally not hundreds. I mean, technically, I'd say there was about 20 ifs, probably nested as deep as 3 to 4. It was like really nasty to work with. And so by kind of flipping around in how you do your recursion, you can make things a lot simpler. So by doing just assuming that we're always at a place in which we need to stop is actually way easier than assuming we need to do our transition and then check to see if we need to stop. And so, yeah, like a lot of these edge cases are kind of captured like in iterate key set. It takes care of all the just nonsense of, okay, you have from 0 to 10, so let's give you 1 key at a time. I kind of hide that away in our do while loop by just using this function. So it just makes things kind of cleaner. So you're only really looking at the walking logic. And so we kind of hit a lot of it via just all these little function calls, like if it is expired, reporting values, walking references, all that kind of stuff. But at one point, yeah, it was pretty horrible. But it just took some time to kind of weed out how we can kind of combine all these things. And there was, like, when we are copying the reference path, or the, what is not the reference path, what do I call it? The requested path on every key set, which is a complex key, like from 0 to 10, and we were copying the optimized path on every key set, well, then there was just a lot more logic on the screen because we had all these extra for loops copying things out like this, but it'd be like right here. So we had another one of these up here. And there's just a bunch of extra things that by just reducing our memory footprint also reduce the amount of ifs, if you will, which is nice.
Yeah, bonus.
Yeah. And do whiles. Do whiles are great. You know, I don't always do while, but when I do, it just makes me so happy on the inside. I can't even explain it. So, you know, you never get to use do whiles when you're really like, this is like the first production do while I've pretty much ever used in my lifetime. So I'm pretty stoked about it.
I don't think I've done one in production either. So
yeah, they're more like, when you do dumb things, you tend to use do whiles, but this is my first time of really actually getting to use it. So it's pretty fun to be able to have time to iterate on a piece of code over and over again. Because I've spent, about 2 months thinking of ways to make the get request lifecycle faster. And so a lot of the improvements we're going in here and trying to figure out how to condense our conditions, reduce copying, and all those fun things. And so, so we can look at how we report values, which once again, huge amount of arguments. I know it's just not the most beautiful thing to look at.
It's not as bad as I thought because you broke it out into a few lines.
Yeah, we tried. Yeah, trying to just stay organized in a pile of disorganization is the best way to go. So, do we? But
if it makes it easier, we have about like 10 or 15 minutes. If it makes it easier to go and have these devices, optimized, you get better value for your user experience, then it's worth it to do those little things that feel ugly in coding.
Yeah. Essentially, I mean, this is for our customers, which are devs trying to build stuff for customers who are paying us. And so, I mean, we just try to do the best we can for our devs. So that way, shout out to Steve McGuire. He's driven a lot of these performance changes. He's a pretty big stickler on how good performance is. And so he'd always come back to me and being like, we got to have it faster. You need to figure out how to make this faster. And so, I mean, we've largely been driven by what devs need. And so we're okay looking at this. Because, I mean, as long as they all kind of have the same, signature, it's pretty easy to kind of work with. It's an internal API too. So no actual consumer of the library has to use this API. So it's kind of okay to have a bunch of arguments for the sake of speed.
Yeah, it doesn't look as dirty as I might have expected from it, so it looks pretty good actually.
Oh, good. I'm happy you've said that because not everybody has said that. All right. Well, would you like to continue on?
Yeah, definitely. But we do have to watch the time. So
okay. Well, we can also. I mean, this is also a stopping point. You know how the walk works. I can show you that in general. If we want to take a pivot, we can look more higher order at. Let's see, where are we at our actual GET request life cycle? If that's more interesting, how essentially we do. I just made a nice little diagram, just in case you guys were wondering how we've essentially made it so that you can request, get stuff from the cache, and go out to the server, get stuff, merge it in, and continue this. If that's more interesting. I don't know. Your call.
Yeah, whichever. I'm liking the code too, so.
All right, well let's just keep on coding then. All right, so when we're on a value type, so now we've landed on something that has a type, or we don't have anything. So we need to report this, or we're at an error. So yeah, either there's a type or we don't have anything. So we're going to report this. So essentially,
this is also in the get folder. Sorry.
This is also in the get folder, and sorry, this is on value type.js. So let's go back to walk path at the very top in our inductive or in our base case. I keep on mixing up the two. I just don't say inductive enough, clearly. So once we don't have a cache, or our cache has a type, or our depth is equivalent to our length, meaning we have nowhere else to go on our path to check for the cache. So we're at this point, so we need to report something. So if our depth is equivalent to our path, then we need to report that we have a missing path, essentially. Like there's nothing here, or we don't have a cache, we need to report it's missing. Or we do have a piece of cache and it does have a type. We need to report this as a value or an error, depending on what that type is. So we jump over and we do all that in onValueType. So we grab our current type from our node, which our node is our current position in the cache. So requires materialize to report is a fun little item, essentially, is that if we have a node and it has a dot value, or we have a node and the dot value is undefined, meaning essentially what this means is that we're going to see something like this. So what this is when you request, say I want movies 0 through 10's title, but I only have 8 movies. Well, what do we do from the data source's perspective? Well, we don't want to give them back only the first 8 movies, because then they go, no, I requested the first 10. Please give me those last 2. Then it would give me nothing. Please give me the last 2. And then it just go in this infinite cycle. So what we do is we insert this dummy data in the cache that says, we requested this data, but there's nothing here. And so that's what a type atom with no value is. It just simply, so you can't insert undefines into the cache. Well, you can, but then they're stuck there, essentially. They're there until you invalidate them and erase them. So that way we don't re-hit the server for the same piece of missing information over and over and over again. So that's its required materialized to report business. And so we have a mode if you want to see all your materialized data, you can actually do a ._materialized. It's an internal mode, but it still is there. And so that's how you can check the cache for stuff. So essentially, we're going to go through all of our ways we report data. If we don't have a node or there's not a type, then we need to report essentially that it's missing. Well, if we ask for this data and it's not there, but we are in materialized mode, then we need to just simply pretend that it's there. We need to omit these bracket type, bracket type type atom with no value. So there is no path here. There's nothing defined, but we're in materialized mode. So we're going to just omit as if there was a value. But if we're not in materialized mode, we'll simply just give a missing path. A missing path adds to the output so that we can go hit the data source, both the requested missing path and the optimized missing path. Now notice here that I'm passing in the length and the depth. That's kind of interesting, and this is the final piece of how we know how to copy our data. So we're going to go to onMissing for a second. Now remember, we do no array copying up until this point. So when we hit this point, we know, okay, we have to create a piece of missing data. And so how we can do that is we can create a requested path by simply slicing up to the depth and concatenating the remaining amount of path left defined. So in case we hit a spot in the cache that just doesn't exist, we just slice to our depth, add the remaining paths. So if we asked for foobar baz, but our cache is empty, we would slice from 0 to 0 and add in the remaining path. Or let's see, is that true? Is that what we do? No, we would slice from 0 to 1. So we'd add in foo, and then we'd essentially get a remaining path, which is bar baz, and we'd concat that all together. Then we do the same thing for optimized missing paths. We slice up to our optimized length, and then concat the remaining path left to evaluate. So that's how we essentially don't have to copy memory in the happy case. If all the paths are there, no copying is needed, as we only copy on missing. Oh, I don't want to exit quite yet. So there we go. So now let's go back to onValueType.js. So we will report a missing value if there's no node or we don't have a type. So if the thing's expired, essentially what we have to do is we have to invalidate the node. So that way our LRU, our least reused, LRU, what is that? Least something cache. Anyways, essentially all it is, it's a linked list where every time you get a node, we put it to the front of the list. When we need to clear memory for the machine, say you put a hard limit at a certain number, once we've exceeded that number, we clear out the tail of the doubly linked list. So that way, everything that you're always getting, we always have at the front of the list. Everything that you're not getting is at the back of the list. We can just delete out the stuff you don't ever get. So that's essentially what's happening right here. That's actually pretty nice. Yeah, so you can actually set it so on a really low memory devices, we can set a really low amount of memory. Like, hey, Falcor, you can only use 1 megabyte. Don't use any more. And we will respect that limit and always be deleting memory as we go. And so if it is expired, we do report this as missing. So you may, if you have a data source, you'll probably want to go back to your data source for an expired item and get the new item. So say it's not expired and we actually have a type. So if we do have a type and it's an error, then this is where things get kind of interesting. That from reference part that I always had. So if we followed a reference and we found an error at the end of a reference, we cannot give just simply the requested path to the reference. We need to give a requested path to the reference and one further. So that's why we have that null check there in the code. That's why I can't delete it. Boom. Is this from reference is required. That so if I let's go back to our little test here, our test file. Go back to this fun piece of information. So if, as you remember, this was our old cache. Well, what happened if Baz, instead of being something nice, was actually a type error, value? I don't know. How about Hunger Games? That's a good error. So we request foobar B. Well, bar is a reference to Baz, which is an error. So if you were to want to delete the error from the cache, how would you delete the error? Well, we would return to you this as an error. If we didn't have this null at the end, we'd essentially return to you an error that has a path of foo bar and then our value would be Hunger Games, right? So oh no, we have an error and this is our error from our cache. Well, that is not true because our error does not exist at foo bar. It exists at foo bar through the reference. So essentially our algorithm also allows for you to add something, a null key, to bypass this whole idea of being able to follow through a reference. And so if you wanted to delete the error from the cache, you would do a model.invalidate. You could essentially use the error we pass back .path. And then it would follow the reference. And then through the reference, we would delete out that error. And so, yeah, that's why we have nulls. And hopefully that all made sense. And if it didn't make sense to me either at first. So
it is a lot to take in.
Yes.
Your examples are helping though, for sure, where you have the test.js and going into the code. Okay, now we add this and this is what it does, and going through. And this is what read the source is all about, I think. Just being go through and figure out, well, what's going on underneath. So this is great. We are out of time, unfortunately. Okay. But this was awesome. I'm planning on playing with Falcor some more.
Cool.
And
if you find bugs, please feel free to log issues. I know we haven't been the most proactive. We've been doing a lot of internal work on it, and I went on paternity leave for a while, so we kind of reduced part of the Falcor. Oh, thank you. We reduced part of the Falcor power of production, so we've been pretty lacking on just addressing all those things just from internal needs versus part of the team being gone. So now that hopefully I'm back, I can help alleviate the pressure of just internal needs, and we can be way more proactive on how quick we respond to issues. But we love pull request. We will merge in anything that fixes our problems as long as you conform to, writing good code, writing a unit test. We're always okay with external contributors. So.
And on the repository, do you have specific labels for people who are new to the project, who it might be easier for them to handle those?
We don't have that yet. I just actually created it this morning. I think I did actually just put it on something this morning. Hold on. Let's just look right here. There you go. PR's welcome. Essentially, someone reported, hey, I'm getting this when I try to get my cache back out. So that way you because Falcor also allows you to serialize your state. So we have a get cache method that's synchronous and will give you all the state of the cache. And apparently it's throwing a max call size. And he even identifies it's because you're grabbing this hidden key that you shouldn't. That's a reference item. Well, I put a PR's welcome on this so that way it's a pretty trivial thing. The person already knows. He already put in the file and what's going wrong. So it should be pretty easy to fix. So Yeah, if I will try to put these on for anything that's a really easy intro that has enough information to just take care of it.
Okay. And is the, for documentation or working on the site, if somebody's, let's say, new to open source in general?
Keep going. I'm confused at the question.
So let's say somebody, like you ever see that there's a Twitter handle like My First PR. Right. And a lot of those things are content creation or dealing with like documentation. Because, some people are afraid to commit code to something as large and complex as something like this. And then that gets them used to the project and they start to see more files and then they can start contributing to other areas.
Mm-hmm.
So something like that.
Yeah, we're completely fine with that as well. We've merged in. I mean, I've personally merged in at least 10, 20 different documentation changes where we were just inconsistent on something. Yeah, we love all that. So we
That's
try
awesome.
to be pretty open with our pull requests. Just just as long as people do the due diligence, and it's pretty easy to tell if you are or not. So yeah.
Yeah. Well, if you're open to it, we definitely should have you back on to talk about some of the other areas because this is really interesting. There's a lot to go through.
Yeah, that'd be great. Please let me know.
Yeah. Thank you so much, Michael.
No problem.